Now we need to consider the input order for NAND gate. We have a choice of the two input, A at the top, B at the bottom, or different way. So we know that for NAND gate, when the other input is one input make a transition, output will go to 0, right? Then depending on this rising edge connected to either A or B, the speed become different. For example, if the A arrives latest, meaning B settled first and then A comes later, then A need to pull down only 6C. But if the B arrives latest, mean B comes A comes first and then B comes later, then B need to pull down 6C and also 2C as well. So such case the transition on B will propagate more slowly to the Y. So we can calculate this delay using Elmo delay model. So if you use the Elmo delay model for this kind of a parasitic, from input A to Y, you can calculate B is already settled to high. So what you have to do is the discharging 6C. So time constant is the pull down is R, right? And capacitance is how many capacitance? 6C. So 2 times 3RC, that's 2 tau, right? If we define the tau equal to 3RC for the inverter parasitic delay. What if we calculate the delay from B to Y, then we assume that in this case A is settled to high first, right? Then in such case the delay would be for the pull down fall, the fall would be what? So the 2C times R over 2 plus 6C times R, right? So that give us a 7RC, right? 7 over 3 times 3RC. So that is approximately 2.33 times tau, right? So we know that the faster propagation must be placed on A, right? The close to the output. So outer input is closest to rail B. So rail means either supply or ground. So that is B, right? Close to ground. Inner input is the close to the output, right? So this is A. So if the input arrival time is known, and so if we know that which one comes first or which one comes late, either A or B, whatever that comes late, we connect that to the inner terminal, so A, so that overall delay is minimized, right? This is the one consideration for logic speed optimization. So a symmetric gate. So in case of the symmetric gate, it favors one input over another, meaning if you want, for example, NAND gate input, we have a input and reset. The reset is kind of static signal. We don't care about that much in terms of the speed. So if you care about speed from A to Y, we first connect the A to the close to the output and make it smaller device size on there, but we get the equivalent driving strength of for example equal to 1. So we had the choice of previous like 2 and 2. Instead of 2 and 2, we make it like a 4/3, and what would be the size for making equal to 1? Let's say that's gonna be, the resistance will be 3/4R, and this will be R/X. That should be equal to 1, so X should be 4, right? If that is 4, then we get the equivalent. So that 4/3 and 4, that gives us the equivalent to 1 driving side resistance of R, right? So if we do that, we can have the same driving resistance, driving strength, but input capacitance is smaller. So we can make it the faster on the input A. So we can, by having this, we know that we boost the size, we increase the size of the non-critical input, for example, recess signal like that. So we can do, as I showed you in this example, we can modify that. So in this case, we can calculate the logical effort on the A and B differently. So total logical effort, the sum of those two will be somewhat different, right? So let's look at the calculation in the next slide. So here, the logical effort for input A would be, what would be the total input capacitance, right? It would be 4/3 plus 2, so 9. So that would be 3/10 divided by 3, because this equivalent strength of the inverter is 2-to-1 inverter, right? For the input B, logical effort is the 4 and 2, that's gonna be total 6 divided by 3, right? That's gonna be equivalent inverter size. So logical effort is 2. So if you add them up for the logical effort, the total would be 28/9. So we can see that the asymmetric gate, for the asymmetric gate, if we try to make the logical effort close to 1 on the critical input path, then we can make it faster. But overall, logical effort goes up, meaning the other path, non-critical path, will be greatly slowed down, right? But we don't care in some case. In that case, we can design this kind of asymmetric gate. Now this time, we can think about the symmetric gate. For example, for the 2-input NAND gate, we know that A and B, input A to Y is faster and B to Y is slower, right? But in some cases, we want to balance those two delay. We want to make it like a same delay for A to Y and B to Y. In this case, we have a 2-2-2-2 size. So we split this to make the delay equalize those two input paths. We split that input device into 2 and connect differently. So we have a like a cross connection there. One has an A on the top transistor, the other one has the A connection on the bottom transistor, and B on the top. So by having this kind of a symmetric arrangement, we can we can make sure that the delay from A and B to Y is the same respectively. Okay. The skewed gate favor one edge over another. For example, let's say if we have an inverter like in the middle, this is a typical equal rise and fall time sized inverter. What if we care about the rise time must be faster? Then we can increase we can reduce the NMOS compared to the PMOS. So overall, the pull-up strength is greater here. What if we care about the pull down? Let's say pull down. The pull down must be faster. In that case, we can increase the NMOS size, right? Such kind of skewed condition, the device sizing can be done. It is totally fine as long as you know what is important, right? If you just scale down both NMOS and PMOS by 0.5 in this example, everything is just scaled down. This is not the skewed inverter. This is just still same on unskewed inverter, because it has still equal rise and fall time, and by having the same resistance for pull up and pull down. In case of the skewed inverter shown in here, we can calculate the pull up logical effort and pull down logical effort separately, because for the pull up we focus on the PMOS device size first. So its equivalent device size will be 2:1. For the NMOS, the smaller one, in that case, its equivalent device will be 1/2 and 1, right? So now the calculation of the logical effort for pull up is 2 plus 1/2. This is the input capacitance, and divided by its equivalent input inverter capacitance, that is 3, right? For the pull down, same input capacitance, 2 plus 1/2, but in this case, equivalent pull down inverter strength is this inverter, so input capacitance is 1 plus 1/2, like that. So we can have a different logical effort for pull up and pull down by having different skew or different sizes skewed from the nominal device size. Okay. The calculation shown here, like for the pull up it's 5/6 and pull down is 5/3. So looking at this graph again, for the pull up device we can find the equivalent inverter size, right, for the same driving strength. For the pull down, we can have this kind of inverter, equivalent driving inverter size. So in calculating logical effort is with respect to equivalent inverter, right? Differently, right? We can apply that differently for those two cases. So the logical effort will be typical logical effort so far we had seen is the same for pull up and pull down. But if you make a skewed gate, then logical effort for pull up and pull down will be different, or for each input will be different. So the definition here is that for a logical effort of the skewed gate will be the ratio of the input capacitance of that gate to the input capacitance of the unskewed inverter delivering the same output current. So we have to find equivalent driving strengths inverter device size. So high skew gate favor rising output, meaning it has a stronger PMOS, right? And low skew gate favor falling output, meaning larger NMOS or smaller PMOS. Differently, we can say that. So we know that logical effort is smaller for the favored direction. So smaller logical effort means faster in the actual implementation. So make a larger logical effort for the less important input. We try to make a smaller logical effort for the critical input. This is the catalog of skewed gate. First, for the unskewed gate, we know that inverter and NAND gate and NOR gate has this kind of a logical effort. But once we skew that, let's say high skew case, we make the NMOS smaller than the unskewed case. Let's say make it half. Then pull up and pull down logical effort will be different, right? And also, we can find that, so for example, if this NAND gate case, if we have a 2 and supposed to be A need to be 2, but we make it 1, for example, in that case, the GU and GD will be different. So GU will be what? How you calculate GU? Input capacitance is 3, right? For example, A divided by equivalent input capacitance would be 3, right? For the pull down, input capacitance is 3 divided by equivalent input capacitance will be, this is the point, this is equivalent to 0.5 device, right? In terms of resistance. So total will be 1.5 input capacitance for the pull down equivalent the input capacitance will be 1.5. So average will be, so 1 plus 2 over 2 will be 1.5, right? So overall, average logical effort is larger than the unskewed gate, but for the pull-up path, we have a logical effort equal to 1, that is a lot smaller than the unskewed gate. We can do the same thing for the low skew gate. Similarly, we can find that. Here for high skew gate, we can determine that here, smaller NMOS, here, smaller NMOS. For low skew gate, we can make it smaller PMOS and smaller PMOS, right? Like that. Then we can calculate the logical effort in the next slide. Finally, we get total logical effort here and here and here, right? I'm not gonna go through all cases to find the logical effort. So now you know that how to find or calculate the logical effort for pull up and the up transition and also down transition differently. So we can now combine those two asymmetric and skewed gate technique. So we can downsize the non-critical transistor and reduce the parasitic delay. For example, if we have a reset signal coming in and actual data from A to Y is important and reset is not critical, in that case we want to make it A faster than reset. So for the pull down path, we reduce the input A but the bottom transistor is increased, but the overall pull down resistance is the same. To reduce the effect of the parasitic from the not in the unimportant input like a reset bar, we have reduced the PMOS device size so that the parasitic added by this reset PMOS is reduced. So overall speed will be boosted without affecting the speed from A to Y, right? So this is kind of the technique when you care about the speed and the okay. So far we have selected the PN ratio same as the mobility ratio, that is 2 or 3 for an inverter. That gives us equal unit rise and fall time because of the same resistance for the pull up and pull down. So alternative is to use the least average delay. For least average delay, we can choose the different PN ratio. For example, let's say we set let's find what is the ratio. Let's say the inverter has the P and driving, it's the same fan out of 1, so it's the same driving output. So ignoring the parasitic delay, ignore parasitic and delay. The full time delay would be for the unit size 1, we have R, the time constants R, and C 1 plus P, right? The load capacitance is 1 plus P. For the rise time, we know that what would be the R, so that would be the mobility ratio. If the P is the same as mobility ratio, then it would be the R, right? If the P is greater than mobility ratio, then resistance smaller. So we can say that this is resistance and times C 1 plus P. So 1 plus P RC, so mu over P 1 plus P RC, right? Now the average delay will be TPDF plus TPDR divided by 2. So you want to minimize this with respect to P. So we are gonna differentiate that TPD average delay with respect to P, and we can find that making equal to 0, that gives us least delay, right? Let's find the answer in the next slide. So we assume in this case, we assume that RC equal to 1. So that gives us the PDF becomes the full time delay P plus 1. Rise time delay will be like this, and average will be those two average, and final equation like that. So we differentiate with respect to P, that equal to 0, right? So round the P, round the TPD equal to 0. That give us what? Like this, P equal to square root of mu. So mobility ratio, for example, mu equal to 2, then P become 1.4, right? This is a little small. This is smaller than mobility ratio for least delay achievement. As I mentioned before, actual standard cell is designed and sized in this ratio, list delay, because they care. They do, in the standard cell, you need to take care of all the input and output, and what it cares is at least the minimum delay, right? We use the PN ratio square root of mu for the typical case. But for custom design, if you care about like equal large and full time, especially for clocks, you know, so we want to make a clock equal rise and fall. In that way, we can have a keep the duty cycle constant, right? Keep the duty cycle right. So for clock we may use that, but for the data we may use that list delay PN ratio as shown here. So the in general case of the best PN ratio is square root of the equal delay ratio, square root of the mu, I mean the square root of the mobility, or the equal delay, equal rise and fall time delay, right? So if you just compare the number you save out of using square root mu times 1 PN ratio, it only improved slightly the average delay, but it significantly decreased area and power. So most of the digital circuit, that's why we have the square root to 1 ratio used actual standard cell design. For inverter, we can, if you use this kind of mobility ratio, we can find the logical effort. That's gonna be 1 plus root 2 input capacitance divided by, for the pull up we get the different equal PN ratio. The equivalent input capacitance of this PMOS device is root 2 over 2 and plus root 2, right? For the pull down GD, we know that input is 1 plus root 2, and for the pull down strength of 1, we have a 3 equivalent inverter input capacitance, right? We can find this like this. As you can see, the number we calculated here for the pull up, the logical effort is just slightly increased, and pull down is less than 1, so overall is less than 1, right? This number compared with the number like 2-to-1 ratio inverter, right? So overall kind of average logical effort is less than 1, right? So it improved slightly the average delay. But the amount of capacitance you are seeing, this is 3C, but this is 2.4 C. So this, if you put lots of inverter there, you will save a lot of power by having this. But for your exercise, for NAND 2, if you have a 2-to-1, the equal rise and fall time size, you get the same 4/3 and 4/3. For the NOR gate, you get the smaller. It was so this is kind of similar to 1. So for the NAND gate, we can keep this logical effort or this kind of a size. But for NOR gate, we know that NOR has typically for equal rise and fall time, we had supposed to be sizing it like a 1 to 4, like a 1 and 1, like that. But this PMOS size is too much. So if we reduce that to half like this, then pull up logical effort as 2 and pull down as 1. So overall average delay is 3/4. This is like a 1.5, right? Compare this number with the original size of the NOR2, you will get for this 5/3, right? This is close to 2, but you get the smaller by having like a 5/3, but this is, you get only 1.5, right? So this kind of a different PN ratio actually can improve the average delay and decrease area and power significantly. So that's your choice, and whether you care about the area and power or whether you care about the equal rise and fall time for both edges. As I mentioned before, typically for the clock path, sometimes you may want to preserve the duty cycle by having equal rise and fall time delay. In that case, you keep the PN ratio with the mobility ratio. Otherwise, you may have a different PN ratio for area and power. Finally, for speed, we know that NAND versus NOR, which one would be better? We know that NAND is better. So, many simple stages versus fewer high-fanning stages. I mean the compound gate versus multiple stage. In terms of speed, the simple stages is faster. Many simple stages is faster rather than the complicated compound gate implementation. And also latest arriving input, we put that close to the output, right? That will improve the speed. But if you care about area and power, instead of a simple stage, you would prefer to have a high fanning stage, meaning compound gate. Compound gate logic would give us a low area and power consumption. Okay, this is the final observation we had seen.